Just at 9. I started the session.
All right, fantastic. Well, good morning and welcome to the session 106, which is about smart charging. This was an interesting project that we took on based on looking around for what could we improve as part of the overall process of the pit operation and what was happening around the actual charging and how could we take better advantage of the pit itself, the structure itself. And the what we'll do in this presentation is I'll walk you through what was the problem, how did we come to a solution, what was some of the lessons learned, and what are some of the future enhancements that we are considering as we move forward from here. So the first problem was that we were really fairly reliant on the classic battery beak that everybody uses. It was almost like people's whoopee in the pit. They felt like that without that battery beak, they didn't really understand what was happening with the batteries themselves. And the battery beak's a great device, but it actually, when you plug it up to the battery, it actually puts it under a load to test the battery, which is the best way to test a battery's health. But at the same time, it just, it was the only way to get that kind of data out of it. The other thing was is that we were looking for a better way to have better pit storage. We had an aging fleet of battery chargers. They were getting old. We'd have to replace them. We knew we had an observability problem when it come around to actual batteries and where the status was of batteries. And then we were manually tracking the use of batteries on a clipboard in a chart that actually someone would fill out what battery was used in what round of what competition, when was it put on a charger, what was the voltage for it, and it was a very manual process that we went through to actually gather that information and collect that information out the battery. In which case, it always led to that key question that every team is asking themselves is which battery is the best battery out of all the batteries you got? So that when you got that one round of the competition that you feel like you absolutely have to have the best battery in the robot on the floor, that was always the question. And people had their opinions about which battery was the best. And generally that had to do with voltage levels or how it tested out on the battery beak. But at the end of the day, what really motivated the team was this, what I would call this fear motivation, which ended up that we would always take around 15 batteries to every competition, which felt like, a good opportunity to improve that and make that a little bit better. So the first thing I was talking about was this use of space. We had a super pit. It had the battery module in it. But what we found was is that there was nothing behind the battery module. So you had this dead space within the cabinet that you couldn't really use. And the chargers themselves actually set behind the battery. So you couldn't see the indicator on the charger itself. And so it was not necessarily an ideal structure of that. So we wanted to look for a better solution so we could have a better use of space in the cabinet itself. And like I said, we had this fleet of like 3 or 4 Real Pro chargers that we had for years. A few of them had like one bank on it wasn't working anymore, but for the most part they worked fine. We were looking at the newer NOCO product and felt like that it had some things to offer, but it was really, really hard to convince team members that to move away from the Real Pro. The Real Pro was, number one, it did charge at 6 amps, where the NOCO product charged at 5 amps. There's always that concern about, well, are we going to be able to keep up with our battery charging in a competition? Then the second piece was, that we found there was a large group within our teams that felt like the Real Pro charger actually charged better batteries to a higher charge, a higher state of charge, and which was an interesting for me because I felt like that's not necessarily the case. At least it's not going to maintain that in any fashion. And so there was that question about, well, what's the NOCO charger going to do in this case? But ultimately, we did decide to go with the NOCO charger pack itself, and we've had good success with it. It worked great. The one thing we did find though is that the NOCO charger has the option to having different battery types because it actually has the logic in it to handle, either AGM or lithium batteries, and you can put it in like a repair cycle. We found that the AGM battery cycle actually seemed to work a little bit better because it runs at just a slightly higher voltage level, which turns out to be more closer to what the Real Pro battery charger does anyway. So we found that the AGM setting worked very well for us. The other piece I was talking about was this lack of observability. So what you really had was you had this indicator on the Real Pro that said it's charging or it's ready. You have no idea where you're at in the middle of that. You're either charging or you got a ready battery, and so that lack of visibility always creates a sense of fear about are we actually going to have a charged battery and ready in time? So one thought there was that we need to put some observability into this in some way that we can actually see what's happening with the batteries and what the actual state of the battery is. But I don't think I could really talk about batteries without really talking about what caused lead acid batteries to die anyway. And the number one problem I know personally I've had is if you deep discharge a battery, like if you let it go to a very low voltage state, chemically it's going to ruin the battery. It's going to be almost impossible to recover from that, particularly in a sealed lead acid battery. It's because of the chemical process of how a battery actually charges and what it does internally to actually to create the charge itself, or you can overcharge them or undercharge them. And the reality is that the Real Pro or the NOCO product is going to make sure that that doesn't happen. It's not going to overcharge the battery or undercharge the battery. It does a pretty good job of understanding when it's in the charge cycle and then moving to a float cycle and then understanding that that battery is charged. So it hasn't really been that problem. I would tell you that you're not really, I haven't really seen a problem with corrosion. It's not like the terminals that we're involved in, and what we're working with has a corrosion problem. You do have to be careful about temperature extremes with that, and that's more to do with storage of your batteries in off seasons. Don't put them in a hot or a cold environment. Keep them in a fairly environmentally controlled environment during your seasons, and you won't have a problem with that. So really, it comes down to what really and truly, in my opinion, actually causes the most damage to batteries is the vibration that happens while it's on board the robot. And so, if you take a huge hit of your robot during a competition or you crash into part of the playing field, then you're likely going to damage that battery. So you got to be really careful with that. I know that even in other devices that I've had sealed lead acid batteries in my personal experience, that's what really ruined them was the vibration itself. I think it has to do with how parts move around within the battery. You sometimes get some deflection within the actual plates in the battery, and then you got a problem or you have a breakage internally in that, and it's going to shorten that lifespan. And that's typically what's happened. I mean, you don't really cycle these batteries enough, over the years to damage them that way. It's primarily the vibration. So you got to be really careful with that with handling of batteries in itself. So let's talk a little bit about the solution design for this. And like I said, one of the biggest drivers was trying to put some visibility into this thing and have better data tracking. So what we decided to go with was these NFC chips. So we found that we could actually just tape onto the battery surface itself a little NFC chip. And there was concern. It was a good amount of debate because we know there can be some challenges with this of putting NFC chips on lithium ion batteries because of the magnetic fields that can get created around the battery while it's charging or discharging. But we didn't find any problem with that with the lead acid batteries. You could you could put these chips right onto the surface of the battery and just use some duct tape or some gaff tape, as you can see, and it worked perfectly fine. And what was really cool about it was the chips also come with, they have about 500 bytes of data storage on board, and which created some interesting ideas about what could we do with that as we went forward. Could we actually, tick some data into the battery itself and store it on board with the chip? And if nothing else, we would have an identifier that would tell us exactly what that identifier was in the past, we had just stuck a piece of tape on the front of the battery and it had an indicator on it, and that's what they were writing in the chart. So we decided to go with the NFC solution, and it worked great for that. The next thing was that we actually built a prototype. So we used like an Arduino, built a little display, wrote some code, got it to work. This is what the first prototype sort of looked like. It was like a status indicator at the top, you know, what was the voltage level, what was the amps that was currently going to the battery itself, and then the 4 number was just the first byte out of the NFC chip that we decided to show on this particular screen. And that it worked. It's sort of a good proof of concept, but we found that number one, the way the circuitry worked, it was pretty complex, and it was like, if you're going to build several of these, you're going to have to deal with this complex circuitry because each component was a different component, and then you had to actually have the Arduino board itself connected to this little LED board, and then have that connected to the voltage sensors. And so it was like, and it was small. It was really small. This little thing is about 1 inch square size, so it was a very small indicator. So we thought, we needed to look for something with a little more visual size to it to try to make that look a little bit better. So we ended up going to this cheap yellow display, and they're not very expensive, but they're really quite cool from how they work, and because they have built into them a lot of functionality. Not only do you have a color display, which that is touchscreen, which is like, in vernacular, totally gas, but then we discovered it actually only had one I2C port, which is not really cool. I mean, if I could tell you that I love the board. I think it's a great platform if you wanted to do some Arduino projects on, but it really does have that limitation where it doesn't have that many ports or the pins that they expose through the connections, and that's primarily because they use up most of the connections on the ESP chip for the memory card, for the display, and for running the LED light and speakers. It has a lot of other functionality on it where if they would make one that had more chips in there where you could have multiple ITC ports or multiple ways of connecting, it would be a really cool platform to actually build things on. But it was a good start, great display, great clarity, great the touch screen was really cool because you could actually have the screen go to sleep and have it come back up alive again. So that became like the cornerstone. Okay, let's build around this particular module. Of course, you had to have the NFC, reader, and this is the standard one, which is the PN532 module, which can do read and write. It does run on the I2C interface, which is actually very easy to work with within the coding. And so that became the two pieces. But because you had only one port, you got to figure out, well, how am I going to talk to multiple devices, because I need to get voltage and current sensors out of that. So we just stuck a multiplexer in the middle of it. So the cheap yellow display talks to the multiplexer. The multiplexer talks to the NFC. And then that allows us to bring in another voltage and current sensor. That is we went with the INA 22.6 sensor, which was, because it was the last component that we picked, it actually turned out to be decently expensive, I felt like, for what it actually did. But the cool part about it is that it did come with that really small resistor inside, which opened up the voltage range that it could handle from 0 up to 36 volts, but it also could handle up to 20 amps of current, which was like, okay, that gives you a lot of options because the other modules did not allow you to go that high. We didn't need 20 amps of current, not from a charging standpoint, because like I said, you typically don't go above 6, if you're using the Real Pro, 5 if you're using the NOCO charger is what you're going to. But you'll see where that comes in later, where that was potentially an option. So that's why we went with that particular chip. So the wiring it up is fairly simple. There's just a straight port on the cheap yellow board. that allows you to connect into the multiplexer. The multiplexer, then you just choose, I used port 0, port 1. Port 0 went to the NFC, port 1 went to the voltage sensor and amperage sensor, and then the charger itself connects, the negative side of it goes straight to the battery. The positive side passes through the voltage to get the current out of it, and then we inserted a breaker, one of those little pop-out button breakers in the middle of it just for safety, and then it goes straight to the battery connector. And then we ran the whole thing on a little 5-volt power supply that would run, because we knew we were going to have more than one of these in the pit, so we could run that one 5-volt power supply and it would run all of them. The cool part about this setup is that it will actually charge the batteries without any of this running. It actually does not require the Arduino to actually function for you to be able to charge batteries. So that's a great feature in that, laying it out this way, you still got the breaker utilized, and you could still charge batteries even if the technology failed in the middle of the whole process. And then you could just rely on the display of the charger itself if you want to see that. So that was a safety feature we had to keep in mind. And the design was we wanted it to run if the technology failed, because technology fails pretty often. So the other piece was that we built this 3D printed this chassis to put the whole thing in. We actually ended up printing it in ABS. It worked out really good. You can see where we used the regular, Anderson connector plug on it. We had little slip-in ports that let you use the WAGO connectors. And then the little box here in the middle is where that's raised is where we had the NFC chip. And the reason we put little edges on it, we wanted to make sure that none of the wiring got close to it, so it would, any kind of interference from that. And then the yellow display fits into the front cover of it. And then I'll explain a little bit more about what these other two holes are at the top, but it just has the rack mounts on the side. The ABS worked perfectly. It was a pretty straightforward print and an actual mount of the devices themselves. So from a price list standpoint, we bought everything on Amazon. It was fairly low cost of each of the components themselves. If you buy them in bulk, like a lot of these things come in a pack of 10. So that gets the cost down really low. But you can see that the really two most expensive things was the yellow display, and then that current and voltage sensor was not cheap. But that's because it has the I2C on it, and it does both voltage and current through that one interface, and that's what drives the price of that up. But otherwise, the other pieces were fairly, inexpensive from that. I did use a cable, which is this USB C panel mount that allowed me to move the port on the Arduino to the front face of the unit itself. So that way we could have a programming port on the front of the unit itself in case we wanted to upgrade the code on it in the future, which we knew we would based on where we were going with it. So it moved that port to the external rack of it, and then allowed you to connect to that. So, all right. So the other piece was, here's what it ended up looking like and with it running. So the display itself, we had a voltage meter on one side. In the middle, it's displaying what was the chip ID that it read off of the battery pack itself, and then what was the amps that were flowing to the battery. And like how many amps was it sending to the battery at any particular time. And then and it worked great. You just slid the battery in, and magically it would pop up with this NFC. It would read the chip, and then when you plugged up your battery into the port on the Anderson connector, then it would just, automatically the voltage would start reading, and then the battery charger would sense the batteries there and what the voltage level was, and it would start its charge cycle, and you could see what amps were flowing into the battery itself. So also the upper left-hand side of this picture is where you see the reset button for the breaker, and then that little screw-on cap with a lid for it. That's where the USB-C port was, that you could reprogram it, as you went, like if you needed to rechange the code on the board itself. So here they all are, just mounted up. We had 9 of them in a rack, and then just beside the rack, on the right hand side of the screen here, you can see where we just had our NOCOs just racked up with that, so you could see the displays on them and get to the buttons themselves on those units. And it racked up perfectly, and we were able to put it on the in the back of the upper shelf of the pit box, so it was really handy and able to see it and see it functioning during the competitions. You didn't have to actually, it wasn't taking up space in the lower cabinet, and it allowed us to actually put an entire new toolbox in the other cabinet where the old battery rack was. So it worked out really good for that. So some lessons learned in this whole thing was, what we figured out was you really only need about 3 or 4 batteries for a competition. You definitely don't need 15. You don't even need 9. This is what we discovered. It's really about 3 or 4. The charger can keep up with that just fine. What we found, the intelligent chargers themselves really sort of handle most of it from a pure charging standpoint. If you really wanted to just uh, solve the observability problem, you could really simply do that with just a voltage monitoring and on a display and put that into the circuit. You could buy this, what I'm showing on the screen, you can buy that right off of Amazon, and it would actually give you the observability you needed about where you are from a voltage standpoint during the charge process. But you wouldn't be able to collect data off of it. But that was just being straight up with everybody, that if you wanted to just solve the observability part, you could do it with a much simpler solution. So what are some future enhancements that we've been thinking about? One is that we could actually collect data on the batteries and the charge events, and actually track that over time and overlay it on top of each other over time, which I think would reveal some interesting trends about how the actual, because if you think about it, the charger throws 5 amps at the battery. That's how many electrons are going in. The battery's absorbing those electrons at a certain rate, and you'll be able to see that on the chart based on how the voltage is transitioning in the charge process. And that it'd be interesting to see over the lifetime of the battery, how that actually transitioned in that place. So it might end up being just more of an educational thing that helps people understand how battery technologies actually work, but which I think would be very helpful. But it truly was not a replacement for a true load test on a battery. So you cannot tell the true health of a battery by just what it's doing during the charge cycle. And that's because of the flow rate of electrons. What really drives a battery is its ability to put out a large flow rate, which is normally in a sealed lead acid battery called cold cranking amps. It's how many amps can that battery actually, put out during a short period of burst of time, which is what you see in a robot when it's actually, either moving very quickly or actuating its devices, during the competition. You'll see that amperage spike of the battery being pulled on that. And what you want to make sure of is what's that voltage lag on that. So the charging piece was not a replacement for how do you actually load test a battery. But that creates an interesting opportunity. The other thing is that we were actually looking at using like a blue mesh for using the Bluetooth low energy that came on the chips, to where we could actually collect that data essentially in a storage in the device, because you can't run a Wi-Fi network in your pit, so you have to use Bluetooth for this. And physically wiring it was not necessarily an option either, just based on the technology. So the next step is we are definitely going to look at aggregating that data into one chip environment that would have an onboard micro SD card, that we could actually timestamp that data with what charger was that battery in, what was the battery, what was the voltage at that timestamp, what was the current, and where are we. And you could do that every second to a base station, and then collect that data across that. So that's definitely one of the future enhancements that's on the list. The other thing is that there's a couple of other ideas that are more short-term, long-term ones was, you know, one is now you got this NFC chip on the robot. I mean, on the battery, why not have the robot detect which battery was on board? And then it could actually, in its data collection, could actually say, hey, this was the robot. Here's what current I drew from it. Here's what voltage it maintained during that process. You could actually collect some really interesting data from the discharge cycle because you can now identify that battery from an an NFC standpoint and understand what's on there. Um, we could also put a display up, but I think there's another good idea of actually creating a test bench for this, which is, and that's where that 20 amps comes in, that you could actually take the battery, plug it up to a test bench with a very similar setup, and actually discharge it up to that 20 amps of load, and then observe what the battery's actual performance is as it goes through that. I personally think that we probably should look for a solution that might get you up to closer to 200 amps or more the higher capacity of what the battery is totally capable of doing, just to see, because I think that would be a really good load test for a battery. But that would be interesting to take that again. You could take that NFC data, collect that information over time. What was the current? What was the voltage level of the battery while it performed that test? And then be able to overlay all that data on not only load test data, competition data, and then also charge data on top of, for this particular battery, how did it perform across all three of those environments? And then you could see what happened with that. From a long-term standpoint, you really could, start to collect data and share that, upload it to a database that in the cloud, and then you can start doing that. You can start doing some predictive health scoring. You could actually have team-wide battery history, that collects that data, like I said, across all of it, which would really help in training, new members that come on board in the future. So that's really it. That's all I had prepared. I don't uh, I don't see any questions on the board. So thank you for your time. And if you have any interest in knowing more about this, you're more than happy to reach out to me. I am a mentor within the First Robotics, and I'm also on the Chief Delphi website. And so if you want to get in touch with me, I'm sure there's ways of doing that through the group. Thank you for your time. Okay, moderator, are we ready to stop?
All right. If anyone would want to, by the way, they can send a Q&A real quick. All right. Should I end the session?
Sounds good. Thank you. Thank you,
All
everybody.
right. Thank you.